Is there something you'd like to talk about?
Use substitution.
Okay, great. What would you like to know? Everything.
How do you better see when to, like, how to substitute or what to substitute?
Yes, so use substitution. If you're going to learn just one or two things about integration, use substitution should be at the top of your list. And it is like the best thing about integration. It's your big tool. And so there's always the big question, how to find your substitution. So there's a couple of notes I should make. And this, I don't know how much I'm allowed to tell you about what I wrote on the exam, but this gets a little bit near and dear to my heart, because I feel like use substitution might be involved in one of my problems, which I only wrote one, so. All right, so how do you think about use substitution? Well, our goal is to simplify. So you're always thinking simplify, simplify, simplify. And you have two variations. You have definite versus indefinite. Let's just sort of, first off, not worry about bounds. So the heart of use substitution comes from chain rule. So everything in integration comes from differentiation. And so what's happening is we say, well, if we temporarily call this our u, and then we say, well, how does u change? We can call this our du. Then this becomes the integral of f of u. This is the danger of trying to write in multiple colors at the same time. Du. So we're trying to simplify. So that's the goal. That's the goal. Now the question, how do you find the substitution? And essentially, the number one thing to look for, the good news is there's only two things. So the number one thing you should always look for is look for a function on the inside. That's always the first instinct. And so in this case, that says you're focusing here, your g of x. So if you see like a cosine of x squared, it's like, x squared's inside the cosine. So here are some examples of things you might see. So if I have cosine x squared, that x squared is on the inside. Integral of secant e to the x tangent e to the x dx. What's the inside? The e to the x. Should we do more examples, or is two enough to sort of convince you? Look for a function in a function. Sometimes it doesn't always look like a function inside a function. Sometimes you might see something like, x squared over x cubed plus 1. What's your inside function? And what is it inside? What is x cubed plus 1 inside of? Yeah, so x cubed plus 1 is in the function of 1 over u. So that's the function where we do 1 over. So sometimes functions on the inside can be a little bit fuzzy. So that's why it's not always going to be what gets it to you. So you have a second thing to look for. Number 2 to look for is you say, I want to have a nice antiderivative. So that's this part. You're saying, is there something that has a really simple antiderivative? So that's because you have to have a derivative showing up in here. So you say, okay, well here, x has a nice antiderivative. It looks like x squared. You don't worry about constants. Constants have a way of fixing themselves. E to the x has a nice antiderivative. X squared has sort of a nice antiderivative. So these are clues that you look for. And so those are what you're looking for. Now there's a couple of notes to make. You have to replace all of the old variable. And pretty much, as long as you can identify and just remember that, you're good to go. Now this includes bounds, if you have them. So these are indefinite integrals. So for instance, we can write a problem. And well, of course, we're very good at writing problems. Suppose we have something like x cubed square root 1 minus x squared dx. Let's say from 0 to 1. This will be fun. All right. Channel your inner, what do we do? What are we looking for? What's our substitution? There's a square root function, so it's like, hey, there's something inside the square root function. So I see a function in a function, that's my first goal. Now, by the way, if all you see is square root of 1 minus x squared, how do you work with that function? So if there were no x cubed in front, so square root of 1 minus x squared, say from 0 to 1. Let's see, can I cover it up in such a way that, my fingers are too big. Curse you, big fingers. Okay, integral 0 to 1, square root of 1 minus x squared. How do you integrate that? Oh, this is just a fun side note. This is not, that doesn't have anything to do with u substitution. It's a circle. Yeah, so if you see square root of 1 minus something squared, think circle. But the x cubed says, nope, not circle. Okay, so u equals 1 minus x squared. So now the ball is moving. So let's talk about various things. What happens to this? Square root of u. Now, we have to talk about derivative. du is minus 2x dx. Well, I say, well, okay, the negative 2, don't worry about that, because you can write this as minus a half du is x dx. So constants are easy to move around. What's our big problem? How many x's do we want attached to the dx? 1. How many do we have? 3. That's the wrong number. Do we give up? Not quite. Say, well, maybe. Let's see another way to think about this. We can say, let's pull an x out to the n so that we have the minus 1/2 du. We still have that square root of 1 minus x squared. And then we have an x squared. Now, remember, we have to replace everything. So we've already talked about square root of u. The x dx, that's minus a half du. Okay, that goes there. I can't leave an x squared there. But what can we say about x squared? Yes, you can use your relationship in many ways, including, hey, I could solve for x, or in this case, solve for x squared. And in this situation, x squared is 1 minus u. All right, now, what are my bounds? Because remember, this dx, that says these are x bounds. We want to go to u bounds. So how do we go from x bounds to u bounds?
You plug in the original value into the u.
Yeah, so we say x equals 0, plug it into u, and out comes u equals 1. X equals 1, plug it into u, out comes 1 minus 1 squared is 0. Are you allowed to go from 1 to 0? Yes, that's fine. It's weird. We prefer to go 0 to 1. So how do you make something switch the bounds? What happens? Change the sign. Notice we already have a negative. So then this becomes integral 0 to 1, and I just get rid of that negative. 1/2 is a constant. 1 minus u, and square root of u, make calculus friendly du. Was this a good substitution? And how do you know if something's a good substitution?
It looks easier.
It looks easier. You can solve it. Anything that makes it simpler, that's progress. That's a good substitution. If the integral looks worse and it's harder, that was a bad substitution. Try something else. And it's okay to be wrong on your first guess. The good news is you won't have very many guesses that you have to make because we aren't being too convoluted. So essentially, look for a function on the inside. If that's not clear, look for a nice antiderivative. So this happens oftentimes with like sines and cosines or secants and tangents. If I see lots of secants and tangents, I say, can I pull a secant squared to the end, or can I pull a secant tangent to the end? Then I can say, I see a nice term that has the derivative of something. That informs my substitution to make. So that's the idea for substitution. Other questions? I know you're like, are you going to finish it, Steve? It just doesn't feel right. You should leave something unfinished.
Do we have to know all of the Riemann sums, like the derivations, like the k squared and all of those that we did the other day?
Do you have to know the Riemann sum derivations? No. What do you need to know about Riemann sums? You do need to know how to find Riemann sums. So the nice thing about Riemann sums is if you think about what they are, there's you're adding rectangles, adding areas of rectangles. That's the idea. And so I might say, hey, let's find a Riemann sum of some fairly simple function. And so in that case, you say, okay, what are you're doing? You have to think about width and height. So do you have a favorite function? Do you have a sort of a function you're okay with? Like, yeah, we get along well, but we only see each other every other holiday. Okay, polynomial. That's nice. Okay, good. Which polynomial?
X squared plus 3.
Okay, x squared plus 3. Great. All right. So you might have a question ask, estimate an integral, right? Because Riemann sums are really estimates of integrals. So we're going to estimate our x squared plus 3 from 1 to 10. Why not? And we'll use 3 equal length intervals. So this is one. I'm showing you some variations that you might see. Do you have enough information to answer this question? And why not? And what else do you need to know?
Do you want us to take the left, right, or middle?
Good. Okay, so this information is telling you about your base. So you're going from 1 to 10. You say split up into 3 equal intervals. If you split up into 3, where are your intermediate points going to be? 4 and 7. Just take 10 minus 1. That's distance 9. 9 divided by 3 says you're going in steps of 3. So you have this x squared plus 3. That's not drawn to scale. And now the question is the height. So you have to be told what height to pick. So we can say, let's use the right end of intervals. So what do? Well, we say, okay, for each interval, now we know what our right ends look like. So it's 3 times our function at 4. So 3 is your widths. Keep your widths about you, so to speak. 3 base height. So there's your f of 7, your f of 4, your f of 10. And you plug it in. So, okay, if you kept going, 4 squared plus 3, 4 squared plus 3, 19. 7 squared plus 3, beautiful number, 52. And 10 squared plus 3 is 103. And we've had problems that are basically just that. So that's one type of question with Riemann sum. Now, the harder question with Riemann sum, excuse me, I got very excited. My throat isn't keeping up. A harder question with Riemann sum says, well, limit as n goes to infinity, your b minus a over n, f of b minus a over nk. This is the integral from, this is not right. Well, let's just do limit as n goes to infinity, b over n, f of b over nk. There we go, that's good. This is the integral from 0 to b of f of x dx. So the question is, if you see this type of expression, can you realize, that's an integral, and then we have tools like fundamental theorem of calculus to solve it. And now, the other question you have is do we have to literally explicitly use the Riemann sum to find an area? No, that's ridiculous. We wouldn't ask you that. We might ask you to say, do you recognize what this Riemann sum is? And then can you turn it into an integral? And then can you give us an answer? That's not unreasonable. You might say, do you need to memorize the sum formulas? So, question, do you need to remember something like sum k equals 1 to n of k is n times n plus 1 over 2? Do you need to remember that? No, it's okay. You don't need to remember that. If you need it, we'll give it to you. And if you don't need it, we probably won't give it to you. So, but you're like, what about, do I need to remember sum k equals 1 to n of k squared? Now, do you need to remember that one? No. But if you need it, we'll give it to you. And if you don't need it, we probably won't give it to you. But maybe we will to distract you. We're devious sometimes. Just sometimes. Just sometimes. I did remember that this is from the review sheet I posted is from an older version of the exam. And there's three topics. Newton's method and L'Hopital. So make sure you know Newton's method, make sure you know L'Hopital. Do you remember Newton's method? Do you know it quick enough to derive it? What is Newton's method? Well, it's a great way to eat a Fig Newton cookie, right? So, this is your formula for Newton's method. Now, when in doubt, you can always rederive it very quickly. Just think about the situation. You have a curve. You say, here's a guess. I want a better guess. How do you find a better guess? Follow the tangent line. That's your better guess. The tangent line looks like y equals the value of the function plus the derivative of the function at that point, x minus xn. Now, plug in y equals 0, plug in x equals xn plus 1, that pops out. So it's just following a tangent line to 0. So if you see a Newton's method problem, you always know it's a recurrence problem. And you just write down the recurrence, plug it in, life is good. How about L'Hopital?
Continue to divide the two until you get to limit.
Can we do a practice L'Hopital where it doesn't start with 0 over 0 or infinity over infinity?
Sure. Which version?
It doesn't matter. Any of the above.
1 to the infinity.
1 to the infinity, huh? Okay. 1 to the infinity. Et L'Hopital, mon ami. Oh, I feel bad. I missed out on the Hopital day. All right. There was a day when we talked about the Hopital, and I was gone that day. Sorry, what?
Our staff is very enthusiastic about like
Well, of course. It's the fun one. It's not like someone's like, okay, now we're gonna, add these sums for the next 2 hours. It's like, oh, the Hopital. Okay, all right. So we'll find the limit as x goes to infinity. All right, let's see. How complicated do you want this to be?
I'll just say exam It's complicated.
I want exam level capabilities. Let's see. Exam level challenges. You're assuming I can remember stuff. I'm old. That's why I don't remember the formula. I remember how to derive the formula. Okay. All right. But okay. We can be serious here. All right. Blah 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 blah. Blah 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 blah. Yeah, all right. We'll do. Let's not go to infinity. Let's go to 0. 1 plus 5x to the 1 over x. How about we do that? Okay, so 1 plus 5x to the 1 over x. Now, whenever faced with any limit, what do? You always plug it in. Always. Because maybe they made a mistake and gave you a simple limit. So, this is going to, this 1 plus 5x is 1. This 1 over x, infinity. Like 1 over 0 basically is blowing up. Okay, and 1 to the power infinity equals? More work. More work. We want to make it that easy. It's indeterminate, which is just a fancy way of saying, I don't know. Okay, so this is not a 0 over 0 or infinity over infinity. Yes?
But doesn't 1 to the power of anything equal 1? Like 1 cubed is 1.
All right.
4 is 1.
I hear you.
So, and 1 to the 100 is 1.
Totally agree.
So wouldn't that also be to 1?
No.
Why?
Well, let's find out. So the real problem is when you plug x equals 0 in, it's currently 1 and infinity. The problem is limits don't care what happens at 0. What do they care about? What happens near 0. Now, near 0, it's not 1. It's like 1.00005 to the million. And 1.00005 to the million is not the same as like 1 to the million. So it has a chance. So that's why there's the ambiguity. Now, I totally understand, It's the same thing as like, isn't 0 to the 0, 0? Or wait, is it 1? And it depends which discipline you're in. The truth is, we define it to be whatever's convenient at the time. All right, now, can we do L'Hopital yet? No. You can never do L'Hopital if you're not getting a fraction that's 0 over 0 or infinity over infinity. So if you do not have a fraction, you cannot do L'Hopital. So when you have more work, make a fraction. All right, so how do you make a fraction? Well, the thing is you want to bring stuff downstairs. What is the bringer downstairs of functions? Logs. Okay, so here's our idea. We're going to call our answer L. And say we're not after our answer. We're going to take the log of our answer. And the great thing about logs, being as it is a continuous function, we can push it through the limit. So this becomes log of 1 plus 5x to the 1 over x power. And we're like, cool. Time for logs to shine. The 1 over x, it's coming down. So at this stage, we have our limit as x goes to 0, 1 over x, log of 1 plus 5x. Are we ready to do L'Hopital? Well, you have to be careful, right? Not quite. It could be, we could tweak it a little bit. Like, as it's written, what does 1 over x do? It blows up. Log of 1 plus 5x, it goes to log of 1, which is 0. But we already knew that was going to not be what we wanted. We're trying to move something downstairs. Now, in this case, it's kind of obvious what moves downstairs. What moves downstairs? The x, because it's already there. What if it's not obvious? Well, spoiler alert, don't move the log downstairs, because that's going to make life painful. We like to be good to ourselves. We are kind people. So don't move the log down, move the other thing down. Now, how do you move the other thing down? Well, in this case, it's very easy. What if this had been like, say, x there? How would an x move downstairs? We'll say it out loud. Now, in this case, it becomes this. But if this had been, theoretically, if this had just been just x, not 1 over x, what would it go downstairs as? X to the negative 1. You flip it over. Like 1 over x flips over. So just remember, you flip it. It's very flippant there. Okay, now we're ready to check again. So we plug in 0. Log of 1 gives us 0. And 0 gives us 0. 0 over 0, which equals? More work. Yes, as someone said, more work, but it's the nice kind of more work. It is our L'Hopital. Ah, L'Hopital, mon ami. Now, you might ask the question, do you have to include this? You don't have to include the more work part. But you should include something that says, yes, I recognize this goes to 0 over 0. Or this goes to infinity over infinity. If you leave that part out, they're going to be like, well, why did you do that? So make sure you indicate that I know something happened. And I like to put in LH, just to emphasize, I know I'm doing L'Hopital. All right. Now, when you do L'Hopital, not a quotient rule. This is the quotient rule we wish it was. What's going to go downstairs?
1.
Yes, it is the 1. And at this point, we are like, game over, man. Game over. Because that is not 0 or infinity. And as soon as it's not 0 or infinity, it's done. But you have to do the upstairs. How do you take the derivative of a log? It's always a fraction. Yeah. Function on the bottom, derivative on top. So 5 over 1 plus 5x. All right, put in x equals 0. And what do we get? 5 over 1 over 1, or 5. Is 5 our answer, and why not? Yeah, you have to remember, whenever you brought stuff down, a log was involved, so really your answer is log of L equals 5, so you use the exponential function to get rid of the log. So that says L is e to the power 5. So that's how you would approach that type of problem. I see a hand up.
When you said x, it doesn't change the function. Wouldn't it be x to the negative 1? X to the negative 1?
Well, what I'm saying is, if you have something upstairs and you move it downstairs, So really, this log became log of 1 plus 5x over, this 1 over x flips to x over 1. So that's what I mean by it flips. Now, if this had been something like x, when I move it down, it would flip to 1 over x. So just to be aware. So never think like, hey, let me move the log downstairs. No, be smart. Don't start. Because your goal is always going to be like, I want to have something where the derivative makes things simpler. And 1 over a log does not simplify. We take derivatives. Yes?
Wait, so the reason we got e to the power of 5 instead of just 5 is because we had to cancel the log you said, or what?
Because this computation was not finding the answer, it was finding the log of the answer. So this shows that the log of the number we're after is 5. Not that our number is 5, but the log of it is 5. So we say, oh, if the log of our number is 5, then to get rid of the log, we use the sort of the inverse to the log, which is the exponential.
That makes sense.
Could you just like an example where the bounds of an integral are other functions?
Like FTC. Okay. All right.
That took too long.
I know. That's about the only time we pull that out. Okay, so fundamental theorem of calculus. Now there's 2 of them, but pretty much anytime we say fundamental theorem of calculus, we only talk about one of them. Because one of them is so ingrained that we don't even think about it. So one version of fundamental theorem of calculus says if you're doing a definite integral, I found an antiderivative and I evaluate. That's fundamental theorem of calculus, but we never think of it as that. It's just like, it's just what you do. So when we talk fundamental theorem of calculus, we talk about things where we say, let's suppose we have the following, where we have a function f of x equals integral x up to x squared of f of t dt. And maybe we know what f of t is. They might give it to it explicitly, or maybe they like draw a picture. So, we can draw pictures. We like pictures. Picture perfect. Okay, so we can draw a little picture here. We'll say this is 1. We'll say this is 1. We'll say this is a half circle, getting us to 3. And then we'll say this is flat. And let's say this goes up at -1 and flat. Something like this. Okay, so they love these types of problems, and they might ask you some various things. Let's see, what's a fun problem we can ask? Oh, I chose poorly. That's okay. What can you say about f of 1? Sorry, what? I heard somebody from the middle. It's the integral from 1 to 1, which gives us 0. Yes, if your bounds ever match, 0 is the outcome. Okay, what is f of 2? Integral 2 to 4 f of t dt. So what do? Well, you say, well, here's 2, here's 4. So you're interpreting it as this area. Can we find that? Yeah, think of geometry. Think of it as like, it's like a rectangle. And what else? A fourth of a circle. It's like a quirkle, a quarter circle.
the radius?
What's the radius of the circle? It's a unit circle, right? Because this is the diameter goes 1 to 3. So halfway. So we say, okay, so it's this rectangle, which is 1 by 2 plus 1/4. How much area is in the unit circle? Yeah, so a full circle would have pi, so 1/4 of that. So there's f of 2. All right, what about, this is a bad choice on my part, and I apologize, f of a half. I know, I chose poorly, but let's just talk about it. We can actually figure it out. We'll zoom in. So, according to this, it's integral from where to where? 1/2 to 1/4 of f of t dt. So zoom in, pull out your microscope. So, okay, so we got our 1/4, we got our 1/2. And so, we just have to figure out how much area there is here. But again, just think geometry. You can say, hey, I can think of this as there's a triangle on top of a rectangle. So for the rectangle, well, it's... Just keep in mind, my pictures are misleading. Distance from 1/4 to 1/2. 1/4. Height, 1/4. So 1/16. Okay, here, 1/2 base, height, 1/32. Add these up, you get 3/32. Okay, so is the answer 3/32? And why not? The bounds are in the wrong order. Orientation matters. So see how you have bigger number, smaller number. So whenever you have the bounds going the wrong way, don't forget to put a minus sign. That corrects the orientation. Okay, but that was not your real question. Let's talk about your real question. The real question is, what's f prime of x? So f of x is this integral. What is f prime of x? Well, so you should have in your back pocket the basic fact, the derivative of the integral from a constant to x of f of t dt is equal to f of x. Essentially what we're saying is, when you integrate, you're finding an antiderivative. If you find the antiderivative, it's like you've moved from here to there, point A to point B. The derivative moves you back. So you're going to get back to where you started. That's why you end up with f of x. Now, you say, but I want more. Great. Let's go from a function h of x to a function g of x of f of t dt. This is chain rule mixed in with fundamental theorem of calculus. What does this become? F of gx times g prime of x looks a lot like chain rule because it is chain rule, minus f of h of x times h prime of x. Okay, so that's that. So, for here, f prime of x, according to this, what would you write down? F of x squared. So it's the 2x goes in for wherever you see the t. Times 2x, subtract f of x times 1. So, here's f. What is f prime of 2? Well, It's f of 4 times 4 minus f of 2. Because I'm just literally everywhere I see an x, I'm putting a 2. What is f of 4? We read it from the picture. It's 1. So 1 times 4, what is f of 2? So it's at the top of the circle, radius 1. So it's 2. So 4 minus 2 gives us 2. So that says, you can use the picture to find areas to help us evaluate points, and then fundamental theorem of calculus to help us evaluate derivatives. And then we say, if you have point derivative, you can find tangent lines. So that's something else you can do. So, all right. Oh, are we done? I guess we're done. All right. Well, good luck. I hope it all goes well.